Thank you, Peter. And can you hear me well? Yes. I do. All right. Okay. All right. So I'm going to be talking today a little bit about protein folding kinetics from the point of view of experiments. And I'm not sure exactly how much of this is clear, known, and how much is not. So as I go along, if you think I'm going too simple, let me know. Okay. And at the same time, if there are any questions, anything, feel free to interrupt, and then we can have discussion. I have a lot of stuff. I don't think I'm going to have time to cover everything, but we can go as we go, and we can see. Okay. Yes, but I think it's more important that we have discussion and things like this than I basically go and talk about all these different things. And as you see, some of these things are very basic, so I'm going to start with the most basic thing, which is, when you do experiments, you have an instrument, you have an experimental technique, you make some measurements. Now, the most important thing here is how you interpret your experiments, your data. And normally, what that means is that you have to use some simple models, and typically, the simpler, the better. And I'm saying this because, in a way, it's one of the reasons why sometimes it's hard to connect experimental work with theoretical computational work, because the level of analysis is so different that sometimes there is semantic discussions or issues about interpretations or things that they have to do more with the models that you use to interpret the experiments and the simulations than really with the facts. Okay, so if we think about protein folding kinetics, normally what people use, sorry, 1 second, let me just clean my glasses because they are foggy. Okay, so from an experimental point of view, the simplest thing that you can do for analyzing your data is to assume that your protein behaves this way, which is obviously a tremendously simplistic model. I mean, it's not really a model in a way because it doesn't tell you much, but it's very useful from the point of view that you can connect this directly to experiments in a very simple way and get some numbers, and that's what why people really like this, right? But the idea is to basically compare protein folding to a very simple elementary chemical reaction. So you said, okay, I have an unfolded protein, or I have a native folded protein, and I have nothing in between. And therefore, I can describe this process with two rate constants, one for folding and one for unfolding. Okay, so this is like the really, really simple thing. And of course, in the moment you do this, this is a very simple model. So your thermodynamics are defined by the ratio between these two rate constants, and that gives you an equilibrium constant. And from here, you can infer a free energy change, which is what people in experiments normally like to report. And then when you think about this from the point of view of kinetics, this is a very simple system to solve. You will have two coupled differential equations. You can build a rate matrix, which is a 2 by 2. You get two eigenvalues. One of the eigenvalues is the zero eigenvalue, which gives you the thermodynamics. And the other eigenvalue gives you this, which is basically the sum of the two rate constants, right? This is in the inverse shape, but it's the same thing, right? This is something that is so simple, but it's important to keep in mind. So anytime you make an experiment where you are looking at a kinetic experiment, what you see is the sum of the two rate constants in the simple idea, okay? So now, well, you go from here into free energy, which I already said. And now, obviously, when you want to do a kinetic experiment, what you need to do is, because, you can do a single molecule experiment, and I talk more about this tomorrow. But if you're doing a bulk experiment, which is what most people do, you have to find a way of perturbing the equilibrium. Because obviously, although everything is very dynamic, when you're looking at this from the bulk point of view, everything is static because it's completely equilibrated, right? So nothing goes on. So what you need to do is to perturb the equilibrium. And you can do this with many of these different things. I'm going to be talking a lot about chemical denaturants first, because that's very commonly used in protein folding, and then about temperature. I won't talk about these things, but it's also possible. Okay, so then if we think about chemical denaturation now, basically the way to do this is you use a chemical denaturant. And here are the two most commonly used ones. I'm sure you all know this, so I'm not going to spend much time here. So you have urea and guanidinium hydrochloride. And these are molecules that are supposed to, the mechanism is not very well known, and this is one of the problems. There is a lot of studies and discussion on how they work. It seems like most likely what they do is they hydrogen bond to the backbone of the protein, and that way they stabilize the unfolded state in which all these backbone groups are not hydrogen bonded well. But there is a lot of discussion about this, and there are obviously other co-solvent effects and things like this. And Sir Angel has, very particular, different opinion about how this works. But anyway, from the experimental point of view, what matters is that you add these co-solvents into your mix, and then you induce a transition towards the unfolded state, and that transition looks like this. And here you're looking at some property that tells you how folded you are, and you see this kind of sigmoidal transition that looks like a first-order transition, at least at first sight. And here you can define this with two parameters. One of them is the CM, which is the value at which of the concentration of the natural value at which the protein is half unfolded. Okay, and then the other one is the slope, which basically is the derivative of the free energy with respect to the concentration of the natural. So it's a very simple model in which all of this is linear, and there is no very clear idea why this is. So it looks like this, right? Which is what I was saying. It's not very clear why this is so, but it seems like for most of the times it's a relatively good approximation, so people use it because it's consistent and it's simple. All right. So once that you have this description, as I said, these two parameters, the M value, which is the slope, and the CM, which is the midpoint, are everything you need to describe the process. And from here you can get the equilibrium constant. From there the probabilities, and from there you can actually get the weighted signal, which would be whatever kind of spectroscopic technique you use to look at the process. Okay. Normally you work in experiments, you work your way backwards. So you start here, right, and you end up getting this, and you will use some kind of fitting and so on. Okay. So this is from the thermodynamic point of view. You will be also interested to do kinetics. I'm just going to skip this, but and here when you want to do kinetics. Now, in this kinetic experiments, what you do is you do the same type of process, but rather than do it in steps, in a titration, and wait for the equilibrium to be attained and then make the measurement. In this case, what you do is you produce a very quick perturbation. And if you're doing chemical denaturation, normally what you will do is you will mix the protein with no urea or one edinium with whatever concentration of one edinium that you want, and that will induce a shift to the unfolded state. Or you could do it in reverse, right? So, so you can do something simple like this, in which you unfold or fold. A protein can be in denaturant, so you can put the protein, I don't know, 5 molar urea, for instance, and then you do a rapid dilution. Now there is less urea, and then the protein will eventually become more folded. And of course, this is an equilibrium process, but the rate of the process, as I say, will be the sum of these two rate constants in principle. Okay, so that's the simplest possible experiment. You can do also a little bit more sophisticated experiment in which you do a double jump. So you start with the folded protein, you unfold it, you wait here for a little bit of time, and then you quickly refold it again. And when I'm talking about unfolding and refolding, I'm talking about the amplitude. I'm talking about what's the net balance in equilibrium. But of course, the process is always determined by the same rate constant. Okay, so how can you do this experimentally? These are the two main techniques that people use. This is called a Stopflow instrument, and I believe I have. Yeah. And here the idea is relatively simple. So what you have is a syringe system with two syringes. In one you have your sample, and in the other one you have the other kind of solvent that you want to mix with. You pump them very quickly using either a step motor or a pneumatic motor or something like this, and then you put them into a mixer. The mixer is typically a T mixer, something in which the two solutions collide. And if the speed is enough, they produce turbulence, and the mixing is quick. And then this mixer puts the sample that is mixed into this chamber, and here you do the spectroscopy that you want to do, right? So you can do fluorescence, you can do absorbance, you can do circular dichroism, whatever kind of technique that will tell you something about the properties of the protein. And then after that, the sample is wasted, right? And then you keep doing this. So basically, this is called a Stopflow experiment because you push, and then you have to stop on the other side. Otherwise, the sample will go away, or it will diffuse back. Okay? And the limitations of this instrument is that, well, first of all, how fast you can mix, but second is how fast you can stop it. And you cannot stop it very quickly because you produce cavitation. And this is why this technique typically has a time resolution of about 1 millisecond, which happens to be not great for looking at many processes in protein folding that I'm going to be talking about more later. Okay? But for most proteins, they fold and unfold completely with rates that are typically slower than that. So that's why this technique has been widely used. And it's also a technique that almost any biochemist will have in their lab, so it's relatively easy to use. A variation of this is what I have here, which is a continuous flow. It's the same principle, but here the idea is rather than pushing hard at a given moment, so like triggering the mix and then stopping, in this case what you do is you are pushing these two syringes constantly at a constant velocity. So there is a constant speed of flux going through here. These two solutions mix again, and typically this mixer could be very different depending on what they are, but a T mixer also works. And then you put the sample into a channel, and the sample is traveling here at a constant velocity. Okay? And what that means basically is once that you mix them, any position in space in this channel corresponds to a time of the reaction, right? Because you mixed, and the sample is moving, so when it's here, it's moved this much, corresponding to a particular time in the reaction. Why is this useful? Well, because you don't have to stop the solution, which means that you don't have this cavitation problem. And also, you can micro-machine this and make it very small. And when you make it very small, this mixer becomes more efficient, because in the end, the mixing time depends on how small the eddies, the little bubbles of solvent you are able to make when you produce turbulent mixing. So this type of technique allows you better time resolution than this one. And also when you're doing micro-machining, that means that, from the point of view of making the sample, it's very useful as well, because you don't have to waste so much. Because you can imagine, this is a normal channel like this, and you keep pushing sample over here to make your measurement, in a few minutes you will waste, like 100 milligrams of protein that it took you like 3 months to make, right? So when you actually are able to micro scale this particular mixers, and I'm talking about channels that are typically 10 microns in depth and maybe 100 microns in deep, so they are much smaller than this, then your sample is not wasted so quickly, and also you can get a faster mixing. The mixing times that you get in this kind of technique are on the order of 100 microseconds. Sometimes you can go down to 20 microseconds. That's your dead time. So how fast you can actually have uniform mixing after you put them in here, right? So these two techniques can be combined, but the experiment is exactly the same. So you take sample of the protein, maybe in 5 molar urea, and you dilute out the urea, and you see how the rates go, or the other way around, right? All right, so when you do this, obviously your relaxation is going to be an exponential or of some exponentials, and this is because typically most processes are in nature are Markovian, especially when we're looking at in bulk, large numbers. And if you have a two-state system, you're supposed to have a single exponential, and this is supposed to be like a big deal and a way of confirming that your system looks like a two-state process. And over here, what you do is very simple. So you get your exponential decay, and from the exponential decay, you can fit it to a single exponential function, and then you get this one parameter, which is actually the average time, and the inverse of that average time, which corresponds to when the signal goes from the maximum to a number divided by E. So typically it's about 0.38% of the original signal. So that value of tau, the inverse of that, will give you the rate, right? Which is what I have here. And this rate is the eigenvalue that I was talking about before. So this rate will be basically Kf plus Ku. Okay? That's the way you do the analysis, so it's really simple. Okay, so now, you remember I said that the chemical denaturation in the thermodynamics are linear with chemical denaturant, so you have basically this linear dependence. It turns out that the same thing happens for the unfolding and the folding rate constants. Typically, not always. And what that means is basically when you do now a plot in which you have the natural concentration here, and here you have the rate. This is a log scale, okay? This is the observed rate, so it's the sum of the two processes, okay? And then what happens here is if you do an experiment in which you start with no denaturant and go all the way to very high denaturant, you will see a rate constant, and as you decrease the final concentration of the denaturant, the rate constant will decrease linearly in a log scale, right? At some point, it will tip over, and then it will do the opposite with the opposite slope. I mean, the opposite direction, also the magnitude may be different, okay? So how do you interpret all of this? Well, the equations are right here. So the idea is that not only the free energy is linear with the concentration of the denaturant, but also the rate constant, the log of the rate constant for folding and the log of the rate constant for unfolding, they also have a linear dependence with the denaturant. And this is done in a way so that the m value that you measure in equilibrium is equivalent to the sum of these two with the inverted sign, because one goes each way. And the reason for these two having the opposite slope is because what you are doing here is looking at the unfolding process from the native state to the transition state, and in the other case from the unfolded state to the transition state. So the transition state is some place in between the two in terms of the sensitivity to the denaturant, and therefore what that means is that you have this type of plot. Okay. From here, basically what you can do is you can determine the mu, which will be in this limb, and you can determine the nf from this limb here, and you can get the folding rate constant over here, extrapolating all the way to the denaturant, and the unfolding rate constant over here. And of course, there are lots of assumptions in here. The most important thing first is that obviously what you're doing basically here is saying, because I have a sum of the two processes, when one is much faster than the other one is the one that dominates. So over here, the folding is faster than the unfolding, so I see mostly is folding, and what I see here is mostly unfolding. Then I'm assuming that this is linear all the way and extrapolating, and this is a extrapolation that is not too long sometimes, but it's key because with low chemical concentrations of the denaturant, this tends to bend over quite often. And the other approximation that is more dramatic is this one, because you're going from very high denaturant and you're extrapolating linearly all the way into here. So these are some of the issues you have when you do these experiments. Okay, so now, in addition to, one second, something I would like to say here first. So when you do these experiments now, you see these two slopes, and the idea is that these two slopes compared to the equilibrium slope, they tell you something about the position of the transition state for folding, right? So you can see here this slope is smaller than this in magnitude, and what that will mean is that the transition state is closer to the native state in terms of the sensitivity to chemical denaturant. Okay, and typically the values that you find differ from protein to protein. In some proteins, this could be actually 10% and this 90% of the equilibrium change. In some cases, it's close to 50-50. And this is supposed to be telling you something of the properties of that rate limiting step, which is the barrier top. Okay. Now the other thing that you can do with this is, you can use site-directed mutagenesis to try to find information about the structure of this transition state. And the idea here is to use the same principles of physical organic chemistry, which is this idea that you can look at the reactivity, and from the reactivity you can infer properties that are related to the free energy of the transition state, and that will tell you some information about the structure if you can connect one with the other. Okay, so when you're doing this with proteins, and this is obviously this approach that Alan first kind of developed. It was created by several people at the same time, or invented in a way, but he is the one that really pushed it. And the idea here is that you can actually make mutations on proteins. And these mutations, if you know the structure, you can make them to be very accurate and make changes that are very localized, and that you have a good interpretation of the structural change. Okay. So when you do this, you produce the mutant. You can do this by site-directed mutagenesis. You make your new protein. You look at the process again. You look at the kinetics. You get this kind of thing, which, by the way, I didn't mention, but this is called a Chevron plot. I'm sure you know. All right. And then you can basically make a calculation like this, in which you see I compare my mutant with my wild-type protein, and I will get a delta G, which will tell me what's the effect in the free energy of folding that the mutation produces. And this is just the destabilization of the protein. Okay, this is interesting because it's our reference. But now the important thing is to look at the kinetics and see how much of this change is happening in the unfolding limb of the Chevron plot and how much is happening in the folding limb. And I can give you an example here. So this is a Chevron plot like the one I was showing before. This is the unfolding rate constant, the folding rate constant. Now you make a mutation. In this case, you're changing this particular residue. You could be making a truncation. For example, you have an aliphatic side chain. You take it off. You leave an alanine. And obviously, that will remove some hydrophobic interactions, some van der Waals, some things like that. And then you can look at the effect. So then you do a Chevron plot for the mutant, which is here in blue. And you have a destabilization. And the way you see the destabilization as a first approximation is by the shift in the midpoint here, this tipping point, right? And if you know the M value from the protein and the M value didn't change with the mutation, which again is a whole set of approximations, but to a first approximation it works, then you can infer the delta delta G, the same one that you can measure in equilibrium, you can measure kinetically by just looking at this position versus this position, see how much in the natural is changed, and converting to free energy by multiplying this by the M value. Okay? And now what you see is the effect in the kinetics, and in this particular example that I have here, you can see that the unfolding rate didn't change at all, right? And the folding rate constant decreased. And all the change is therefore here. So what's the implication for this? The implication is that whatever you made with this mutation changed the energetics of the folded protein, but didn't change the energetics of the transition state in the same way. Okay? Because you don't see any change here, so that means both have been changed the same, and you see all the change in this other limb, which means everything is from the unfolded to the transition state. And that's what people will call here a phi value 1, which is fully folded at the transition state. So what the implication here is that the mutations that you made change interactions that are all formed in the transition state. Right? You can have the opposite effect, in which this limb doesn't change and all the change is here, and in that case you will have a phi value 0. Okay? And of course, you can have anything in between. Even though in the beginning, when Alan first was thinking about this for the first time, he was only thinking about these two string cases. But obviously it turns out, and I don't have to tell you here this, because Peter was obviously one of the persons that were really pushing this forward, the intermediate values are the ones that you should expect by definition. Right, so how do you look at this data? So the way I find most accurate and most informative is to do this kind of Bronsted plot. Again, Bronsted is this guy from physical organic chemistry a long time ago. And the plot that he proposed is to do something like this, in which you're plotting here the delta delta G in equilibrium, which basically means the change in the free energy produced by the mutation from the thermodynamic point of view, right? So this is the shift in the midpoint that I was telling you about. And here what you're plotting is the change in the kinetics. And here you can do two different ones. You can do the kinetics of unfolding or the kinetics of folding. And depending on whether you do one or the other, this will be inverted. But in this case, what I'm plotting here is the change in the unfolding rate constant. So what you can see here is that in this plot, if you have anything going in this line, will tell you that your phi value is 0, right? So that means that you don't change your unfolding rate constant. If you go along this diagonal, your change will be 1. That means everything is happening in your unfolding rate constant. And anything in between will be appearing over here. And of course, all of this is for destabilizing mutations. And here will be if the mutation happens to stabilize, which sometimes is more rare, but sometimes it happens. And in that case, an intermediate value will go over there, the 0 will be over here, and then 1 will be going over there. Okay? So this is kind of the idea. And I like this plot much better than defining, just looking at the phi value, because the phi value has a lot of error. And these are convoluted mixed errors, so which is hard to distinguish. When you at least make the plot like this, you can see how confident your data is. For example, you can see here that if you are making a big change in free energy, like for example 20 kilojoules per mole, you have a big dynamic range here, right? But if you're making a very small perturbation, your dynamic range is very small. So this measurement here is going to have much more error intrinsically than this measurement here. But at the same time, there's another problem, which is proteins are relatively flexible and they are not very stable. So you make a big perturbation like this, and this is a big perturbation because normally the delta G for a protein is typically from 15 to 40 kilojoules maximum. So making 20 kilojoules, I mean, for some proteins, this is actually like a bomb For other proteins, it's still huge, right? So then you have to play a little bit with this too, right? So you make a big perturbation, you have better dynamic range, but then you may be distorting the process so much that all these assumptions don't work anymore. If you make a small perturbation, you are being more conservative, but now you may be actually fooled by the intrinsic noise in the system. And let me just show you what I mean by this. So these are two simulations. This is not data, right? So what we did here is a very simple simulation in which we generate a whole bunch of possible mutations. And each of them has a different value of free energy. And we pick this according to what you see experimentally typically. And you have a change in the unfolding rate constant that is fractional. And this is also randomly selected. So this is a scenario in which this kind of approach will give you the maximal information in terms of the structure, right? And those are the red points, by the way. So every value that you do, you make a mutation, you produce an effect on this axis, and then you have an effect on this axis. And of course, you will see something that looks like that, covering everything nicely. That means that your mutations are really telling you a lot about the structure. Okay? So this is scenario number 1, maximal structural information. Now, this is the opposite scenario in which you say, what if all my mutations give me just one value, always the same? Okay? And a value is this red line, which I did choose here 0.3 for reasons that are going to be obvious in a moment. But okay, that's the other scenario. Okay, so now what are these blue dots? These blue dots are just basically a simple analysis or propagation of the typical error in these experiments. Okay? You have an error in the determination of this delta G, and you have an error in the determination of this delta G. This one is typically larger, by the way. And when you put these two errors, I mean, and this is obviously a kind of a conservative calculation because I'm assuming that the error is kind of distributed uniformly. Sometimes the error is more in some particular experiments than in others, in some particular protein versus others, and so on. But in this case, basically, the blue dots are telling you how this plot will spread out just by having a conservative inclusion of the errors that you have in the experiment. And you can see here, obviously, it doesn't seem too dramatic. You know, you still have, you know, things are obviously still spread out. Obviously, you get over the plot, and you get over, and these are what people will call non-canonical Phi-values. By the way, this number is called Phi-value. I didn't say, but these non-canonical Phi-values are values that are not 0, 1. They are either smaller than 0 or higher than 1. And obviously, those are not called non-canonical because it will imply, if they were true, that the transition state is not in between the folded and the unfolded state, it's somewhere different, okay? And that's normally not what you find. But of course, you can see here that, you know, you can find non-canonical values, especially over here, just because you have a lot of error, okay? Now, what it gets interesting is when you look into this particular plot here, you have only one value for every single mutation and every single protein. That's kind of the assumption in this calculation. And then you put this error, and then what you see is something like this. So what's the first clear implication? When you are in this region here, there is no way to tell, right? They both look the same. So what that means is that, and this is something that several people have said, I have said this, but several people said it even before me, which is basically, if you have a perturbation smaller than maybe 7 kilojoules per mole here, right? There is no way to get any structural information whatsoever from this analysis. So if any of you, I mean, people don't do this anymore so much, but, you know, some of you or people in your groups from before were doing this for a living for many years, you know, you shouldn't look into numbers that like that, all right? Because they don't tell you anything, and you will be trying to predict noise, which is not easy to do. And it's also not very informative. Now, this is the silliest possible simulation. I'm just generating random numbers and applying some experimental error as white noise, basically. Very, very simple. The error is probably more than this, by the way. This is we try to do this conservatively. And also here is uniform, and in some other cases it may not be uniform. Now, how does this compare with the real experiments? Well, this is what the experimental data from 24 different proteins. I don't have it here, but there's 24 different proteins, 806 mutations. On the average, 30 mutations per protein, roughly. And what we did here is the same Bronsted plot. So this is picking the numbers from the bibliography, right? So these are real experiments. So this is the delta G in equilibrium. This is delta G for the kinetics of unfolding. And here what you can see, and basically, by the way, this is colored in 3 layers. So the one standard deviation away from this line, which gives 0.24, by the way, is in dark green. The second standard deviation, 27%, is in the lighter green, and the last, anything beyond the second standard deviation is in white. Okay, so what you can see, this data looks awfully similar to the scenario in which there is no structural information whatsoever. Or basically meaning everything there is to see is an average Phi-value. This average Phi-value is 0.24, which is also an interesting thing to remember. So that means that basically, on average, your protein is going to have a transition state in which 25% of the energy of interactions is not made yet, and 75% is already made. Sorry, the other way around. 75% is not made yet, 25% is already made. Sorry, I said it the wrong way. Okay, otherwise it would be hardly a transition state. Okay, so and this is an important number because it's coming as an average from everything, and in principle, all the information that you can get is there. You can see that you have the white points normally are non-canonical. Why? Because they're just coming possibly because of error in experiments. And the only numbers that may be useful from a structural point of view are these guys over here. Or not, we don't really know. So there are a few, maybe 3% of the mutations that may tell you something about the structure. And those may be really interesting. But the problem is how to weed this out from all this other, noise. And here, this is just a plot of the 24 proteins separately. So these are independent mutations for every protein. You can see that overall the trend is maintained. The slope is pretty much the same. Obviously, some data sets are much more linear. Others are a little bit more spread out. This may have to do with the protein being a little bit more different. May have to do with the type of mutations that the people make. This is another very important point. Some people make some mutations that are conservative, like, for example, truncations. So you don't introduce anything new. You just remove stuff. Other people make mutations that are a little bit more cavalier, right? And they just try to put a polar residue buried. And it turns out that most of the mutations that have unusual Phi-values, by unusual meaning deviating from this line, they tend to be mutations that are kind of more drastic. Okay. And as I said, this is very important because this was one of these key measurements that we had on how to protein folding looks like from the point of view of experiments, and it's been used a lot by theoreticians to try to understand the process. Okay, now the values that I was showing before were at in native conditions. Okay, and this also implies a little bit of a problem if you think about it, because the native conditions are different for every protein. From a thermodynamic point of view, native conditions are whatever the delta G of the protein is in native conditions, and that varies. Some proteins may have 15 kilojoules of stability, some proteins may have 40. So you are actually comparing things in a different thermodynamic state, right? So now, once that you have compiled all this data, something that you can do relatively easily is to actually propagate the numbers at different degrees of thermodynamic stress, or basically different degrees of stability. For example, you can go back and say, what happens now if I look at all the proteins at their folding midpoint, at this, the bottom of the Chevron plot. In that case, my thermodynamics are the same for all, right? So I'm already conditions that both states are stable, equally stable. And in that case, what I see, and this is the phi value, and what I mean here by iso means there's the slope of the plot, okay? So it's the average phi value for everything. So it's actually of the order of 0.35, all right? So it's a little bit higher. That means that the transition state has become a little bit less native. A little bit more native, excuse me, I'm saying it the wrong way. It keeps changing, all right? So this is more or less the values that we find in native conditions. And what we see here is something that people call the Hartmann behavior, which basically means that the phi value increases as the protein is destabilized. So basically what that means is that as you are tilting the landscape towards the unfolded state, the transition state is moving away from the native state, right? It's getting closer to the unfolded state. So that's what this is. We can see that all proteins do this. So this idea that we have a defined transition state is bogus. Transition states obviously change depending on the conditions, and you should be, and this is something that in the early times, sorry, one second. The assumption was that these n values didn't change, because if the n values change, you can immediately realize the phi value is not a constant, because it will depend on what concentration of the natural you use. Now we know that the n values, the slopes, change constantly, and that means this behavior is there, universal. Yes. Yes, definitely. It's possible. But remember, here we're doing experiments. We don't know what the reaction coordinate. The only thing we know is that this is as a function of the denaturation process induced by chemical denaturants. So this will have to do with the accessibility to the solvent of the protein, how these co-solvents can get inside, and all these different things. And as I say, the problem is all that stuff is not very well known. And so there's not an easy way to rationalize this from a pure physical chemistry point of view. But the observation is this, and the other thing that is kind of interesting is that here in red what we are plotting, and this is the scale, is actually the standard deviation of the data. So how close to the line it is. So when we go to very stabilizing conditions, very native-like, the standard deviation is minimum, which means everything looks pretty much the same. As we go to more destabilizing conditions, this increases, and increases quite a lot actually. This spreads out. So what that means is that there is probably, part of this is propagation of errors, obviously, and you have to be careful with that, but part of it also means that, if you want to get more information about the transition state, you want to go to conditions that are more destabilizing or less stabilizing. Okay? Yes? I was going to tell you more about this, but with temperature. And I see that I have only 22 minutes left. So, because I have a whole bunch of stuff here with a different type of model. I don't know whether it's a good idea to discuss it. And I like to do it, first of all, because we use the model, but also because it's kind of a little bit more, it's still a very simple model, but it's sophisticated enough so that some of these things can be predicted rather than inferred directly from the data. But I like to talk about what you were saying, which is what happens when the proteins have smaller barriers, and then it becomes a little bit more delicate. Okay. So I'm going to skip this for a moment. We may go back. All right. So I'm just going to go here now. And if we have time, we can go back to that. All right. So now, all that idea is using chemical denaturants and proteins that are relatively slow folders. And by slow folders, normally what we mean when we're experimentalists is that there are proteins that fold much more slowly than 1 millisecond, so that you can do Stopflow measurements and you can do all the experiments that I was talking about. Now, there is another class of proteins which are fast folders, and fast folders means that folding and unfolding rate constants are much faster than 1 millisecond, and therefore you need different methods to look at them experimentally. And also, they behave a little bit differently. So in this case, obviously, and I don't have to talk much about this, but the idea is, I'm going to talk a little bit about rate theory from the point of view of experiments, right? So normally, and this is something that we can do nowadays with certain confidence because of Jose's and Peter's work on this. The idea is that you can get all this complicated energy landscape, you can project it, right? And here goes to the reaction coordinates that I guess Jonah was talking about. Here the idea, obviously, the stream projection would be one reaction coordinate, single order parameter that behaves like like a reaction coordinate, ideally. And whether this is possible with one, still debated. And for some cases it may work so, for others it may not. But just from the point of view of the principle, this is the simplest thing that you can do, just from a rate theory point of view, right? So in this case, you will have a free energy surface, which is the projection of all this landscape, right? this free energy surface will have, if you have a two-state system, it will have two minima, the unfolded and the folded, and it will have a free energy barrier in between. Okay. And of course, now you want to try to understand how this is related to the rates. First thing that you can do is this kind of equation that comes from this paper and the work in the late 80s, early 90s from Peter and Jose, in which basically what you can say is that your characteristic time for folding is proportional to the something like this, which is like a pre-exponential, times the exponent of the free energy barrier. Right? This tau naught is basically supposed to be in their treatment something related to the motions or the time scale for the motions that are required to cross the barrier, and that in kind of fuzzy way, right? Now, here there is some. Here it says condensed phase reaction. Sorry. Okay. So now it turns out that you can actually compare this very nicely with the Kramer's rate theory for condensed phase processes. And in this case, what you have is something that looks like this, in which this can be equated to something like that, in which the barrier term is the same, and this tau naught is now has this form, in which this is the diffusion coefficient, so going over the barrier here, and these are the curvatures of the well, and the barrier top, the inverted curvature. Well, it's actually the square root of the curvature, by the way, and obviously this is better. So this kind of relationship allows you to look at this into a little bit more sophisticated way, and now we can look at kinetics rather than with the simple models that I was telling you about, with something a little bit more informative, a little bit closer to theory. Okay. And you can also look not only at the rate, which is basically the time it takes to go from here into there, but you can also look at the transition paths, which is basically the time it takes to cross the barrier once that you are committed to cross the barrier, which in this particular diagram will be to go from here to there. And this is kind of arbitrary in a way, but the idea is you can immediately see that you are doing this very, Brownian motion. Eventually you're going to be going up and down several times, and eventually you'll go over. But as you are going over here, you also have a chance to go back. And the transition path is basically the time it takes you to go all the way without returning. Okay. Now, and by the way, so you have also an expression. This is an approximation coming from Attila's Dabo, in which you can get an idea of this transition path time, which is basically almost independent of the barrier, not completely independent of the barrier. It has some dependence on the barrier. You can immediately imagine that if the barrier is higher, transition path is going to be a little more, longer, right? But the dependence on the barrier is very small because this is dependent on the log of the barrier rather than on the exponent of the barrier. So it's very little dependence, and mostly this transition path depends on the diffusion coefficient and the shape of the free surface. Okay. So now you have experiments in which you can look at kinetics and you can get this information, and then you can do other experiments in which you can get this information. Then you should be able to get much more out of the experimental measurements. So this is what you can do with fast folding proteins. So the first part that I'm going to talk a little bit about is about the kinetics, and this is still very simple. Okay, so if now you imagine that rather than using chemical denaturation, we're using temperature. And why are we going to use temperature? Because fast folding experiments, the fastest ones that you can use typically are laser T-jump experiments. And in that case, I'm going to talk a little bit more about that in a moment. In that case, what you reduce your perturbation is a jump in temperature, right? So you heat up the sample, and because folding always encompasses a change in enthalpy, that means there is always a temperature dependence. You all know that. So in principle, it's a universal method that you can use, and this is a method that you can use and is much, much quicker. So you can make measurements in nanoseconds or even some nanoseconds sometimes. So you don't have this limitation. So it's a perfect technique for fast folding proteins. Okay. Now, when you make those experiments in which you're changing temperature, obviously you're going to measure a rate, which is the relaxation rate, the sum of the two, if it's a two-step process again, and it's going to be temperature dependent. But now here we have a better understanding of how this is supposed to go. Not perfect, but better, because we can take this now and using Nernst equation, and we can expand this, and the temperature dependence will look a little bit like this, in which basically the only thing we are doing is using Nernst equation, so there is a change in enthalpy, which gives us the, you can see So this is the slope for the temperature dependence, and we have an entropy change. Sorry, this is the slope, and this is the intercept. And then if there is a change in heat capacity, which is normally something that you find in protein folding, because the unfolded state has much more solvation than the folded state. And what that means is that the enthalpy the enthalpy is not constant, it changes with temperature, and you have these entropy enthalpy compensations. Anyway, so you can take the equation and it looks like that, okay? And as I said, this is for either the folding or the unfolding rate constants. When you're making your measurement, you will be looking at the sum of the two. So you will have to find a way of deconvolving one from the other. But let's assume for a moment that you can do that. Now you will have an equation like this, okay? And it looks interesting, nice. So what you can do now is your experiments at different temperatures, so you can see how the rate changes with temperature. And from that, you can try to get all these parameters. Of course, these changes in enthalpy are related to the transition state, from the unfolded to the transition state, or from the native to the transition state, right? So you can determine the change in enthalpy, the change in entropy, and the change in heat capacity, in principle, right? Now the problem is, if you actually put this into a form, polynomial form like this, in which these coefficients are basically functions of all these terms, what you find is that there is a little bit of an issue here. For instance, you can see that this is roughly linear with a curvature. The curvature is depending on this A2 term, right? Because it's a log of x. X is the inverse of temperature in this particular case, okay? So there is a linear term to the 1 over t, and there is a logarithm of 1 over t term as well. So this term you can get right away because this curvature is in this kind of model, which is, again, two-state, but with temperature dependence. All this curvature is going to come from the delta Cp term. So that means that you can actually get this from the experiments right away, okay? And of course, depending on the models, this may not be just pure rate capacity, it may have other things like frustration and things like that, but anyway, in this simple model, that's the way it looks. Now, if we go to the second term, which is the linear term, we can see here that we can actually get it as well. Why? Because it's the function of the sum of these two. We already know this one from here, so we can get this one, right? So it's also well defined. The problem goes when we go into the A naught, because the A naught is actually dependent on both the pre-exponential, this, which is the same thing I was talking about before, and the delta Cp term, and which we already know, but also the delta S. Okay? So what that means is there is no way from here to get this and this. And this is one of the big problems. And in the old times, actually, people were using a number for this value coming from gas phase reactions. And actually, they were using the frequency factor from Arrhenius theory to try to get all these numbers. And of course, the Arrhenius frequency factor is 10 to the 13 per second. It's something that doesn't make any sense for condensed phase, much less for a polymer moving with a lot of solvent. And that means that all the numbers that people were getting in the old papers were all kind of wrong from that point of view, right? So, but the big issue is here, how you deconvolve all of this. And this is where fast folding experiments, come a little bit to the rescue to some degree, which is, if you can have a good estimate of what this is, you should be able to at least get some information about the barriers and decompose the entropies and the enthalpies. Of course, we couldn't measure this directly, but we could, using fast folding experiments, we could get some estimates of the prefactor term. And this is something that several people, including me, have been working for 15 years. They're trying to get different ways of estimating this prefactor. Here is some list of numbers that come from different experiments. For example, some of the ideas, and this goes back to the Onuchik-Wollines, the Sochi paper, basically saying that, obviously this corresponds to the fastest, to the fastest possible motion that takes you over the barrier, right? So you could say, definitely a protein cannot fall faster than what those motions are. So, for example, you could imagine saying, I'm going to assume that folding cannot be faster than making just a loop, right? So if I can measure the rate of loop formation, then I will have an estimate for this number. There are always going to be upper estimates, okay? So remember that, because you are looking at processes that are supposed to be as fast or even faster. So loop formation gives you 10 to 20 nanoseconds, And this is experiments that have been done by Lapidus, Eaton, Bieri, and Keith Faber, several other people. Okay. Now, another property that you can think is, okay, protein folding cannot be faster than the rate of collapse. And we have some idea how the rate of collapse should be, coming from polymer physics and so on. And the numbers, the theory actually predicts things in the order of 20 to 100 nanoseconds. And it turns out that the experiments looking at non-specific hydrophobic collapse, and this is our work, give you something of the order of 100 nanoseconds. Okay. Now, it also turns out that protein rates for folding and for unfolding scale with size. And this is something that has also been found. Tirumalai has worked on this. Filkenstein has worked on this, and we have worked on this as well. And I will have talked a little bit more about this with the model that I was talking about before. But let's keep it for the moment. But the question is protein folding rates or protein folding times scale with size, not linearly, it scales to an exponent. But the nice thing with this is that you can obviously propagate this to the 0 size, and that will give you the pre-exponential as well. And in here, when you do that, and this is some work that we placed in JAX in 2005, gives you something of the order of 1 microsecond. Okay? You can also look at the relaxation dynamics on the unfolded well. And of course, this is going to be an upper estimate, but if you can measure the dynamics of the protein when it's unfolded, you know for sure that the protein cannot fold faster than that. It should actually be slower. So from these experiments, or looking also at from the top of the barrier, I'm going to talk a little bit more about this, which is Martin Grubel's work. He published a paper in Nature in 2003. In this case, what you're looking is at the relaxation from the top of the barrier down. Okay? And in those cases, you get numbers on the order of 1, 2 microseconds as well. You can also try to get an estimate from, this is the other way around, this will give you more like an upper estimate, sorry, a lower estimate, in which you say, okay, let's try to look at the proteins that are the fastest I could ever possibly find. And let's see what rates they have, right? And this is what we, basically this work from a lot of people, Martin Grubel, Eaton, Hagen, Fengai, ourselves, or even looking at downhill proteins, which are supposed to be barrierless, so the rate is just dynamics, so it gives you directly the pre-exponential, or something similar to that. In those cases, what we find is that the fastest possible, faster folding proteins are in the order of around 5 to 10 microseconds. Okay, so all this I took a long time to compile, but it gives us a scale, right? So we don't know exactly what the pre-exponential is, but we know the range, and the range is now